In this video, we will go over a segmentation architecture called DeepLab. And this is pretty close to the state of the art. And we have used this architecture many times in our consulting work as well. And the first time I saw the results from this paper, I literally fell off my chair. It looks like science fiction. They are so good. And when we actually used it in our own work, it lived up to the expectation. So if you have a segmentation task that you want to solve, try training DeepLab v3 or the better version after that one. But DeepLab v3 has been used very successfully in a lot of our projects. It works really well. So let's go over the architecture. Now, the basic idea is that they use the VGG16 backbone and they use some of the convolutional filters. They are replaced by dilated convolutional filters, and we will talk about that. And in version 1 and version 2, they use something called conditional random fields to enforce spatial consistency. But in v3, they remove this. So we are not going to go over conditional random fields just because, the latest architecture actually doesn't use it. But version 1 and version 2 of the architectures did use conditional random fields for refining the results. Now, let's just recap what is dilated convolution. So here we are looking at a 3x3 convolution filter. If we want to dilate it, it looks something like this. We are essentially adding holes in this filter, and this way we are increasing the receptive field of this convolution kernel. And dilated convolution is sometimes also called a true convolution. It is a French word, true, that actually means holes. So that's where the name comes from. But in most of the time when I talk, I just use the word dilated convolution because it is easier to pronounce. And also because there are only 2 times in my life when I got a C in a course, and French was one of those cases. Anyway, let's move on. So the important thing to keep in mind here is that dilated convolution allows you to capture a bigger context without changing the size of the calculation. So we are capturing greater context at a coarser resolution. That's the trade-off we have made. But we are doing the same number of calculations. So in this case, when we convolve this filter, we are essentially multiplying each pixel patch with these 9 elements, and we are doing the exact same thing in this case. There are 9 elements which are being multiplied. Let's see an example how dilated convolution is related to regular convolution and how it affects. So this is a picture from the paper. They used regular picture, then they downsampled the picture to about the 1/4 of the resolution, and they applied a gradient filter to it. So this one is a Y gradient filter. If you can look at it, red area represents regions which are positive and high, and blue regions represent, pixels which are dark and pixels which are negative. And that is why this is a gradient filter. You must know this from course 1. Now, if you apply this filter to this image, you get a map that looks like this. Again, this is a heat map. Wherever we see red color, it means that it is high positive value. Wherever we see blue, it means we have low negative values. Now, if you want to get back to the original size, we have to upsample it. And if you upsample it, you can see that there are a lot of holes in this upsampling. Now, there is a second option. What you could do is, instead of changing the resolution of the original image, you could change the resolution of the filter. So here you've upsampled the filter, but it's a very coarse upsampling. So essentially we have done this kind of upsampling. We have taken and added holes in between the filter and not really done bilinear upsampling. It is basically adding holes and the various elements are still there. Now with this kernel, when we apply this to this image, we get something like this. and you can see that this is a much smoother approximation of the feature map. So the point is that instead of downsampling the image, you could also use this dilated convolution to get the exact same result, except that you get nicer results, smoother results in this case. So let's see how we use dilated convolution in this architecture. But as I mentioned that we are using the VGG16 backbone for DeepLab. You could use different backbones for this DeepLab. VGG16 is a popular one. ResNet, people use it as well. So let's look at the VGG16 backbone because it's the easiest. Now this one is the standard VGG network. We have a bank of convolutional layers. So this is a convolutional group. It itself has two convolutional layers, usually a max pool layer. I'm just calling the whole group as C1. Similarly, we have C2, C3, etc. And as it passes through the network, the image which starts, say, at 224 by 224, it gets reduced in size progressively. So it reduces by half again, by half, and then all the way to 7 by 7 as it passes through these 5 convolutional groups. VGG16 has, as the name suggests, 16 layers, and out of those 13 are convolutional layers and 3 are fully connected layers. We are showing only 5 because these are groups. There are 2 convolutional layers in C1, for example. So just to simplify things, I'm representing them as 5 groups instead of showing all the 13 layers. Now, so this is the standard VGG architecture. Let's modify it for n number of classes instead of 1000 classes. So all we need to do is change this last layer and put an n here. Everything else remains the same. Now, this is DeepLab V1 architecture. We are going to build it out, but let's see how we have changed the VGG16 backbone. First of all, if you notice here, the size of the volume still decreases as we go through the network. It starts with 224, goes to 112, 56, 28, and then we make some modifications to the network so that the size doesn't change anymore. Let's see what are those modifications. So C4 and C5, we have removed the max pooling layer of stride 2 with just a max pooling layer with stride 1, or you can completely remove the max pooling layer. The idea is that the max pooling layer, when we use a stride of 2, it decreases the size of the volume, the size of the feature map by 2. But if you just use a stride of 1, in that case, there is no downsampling of the image with appropriate padding. So now these 2 layers have been changed. So we don't go all the way to 7. In the original architecture, you can see that the size was reducing to 7 by 7. We don't want that. The other thing that happens is that the convolutional filters in these 2 layers have been replaced by dilated convolution filters with rate 2. Now, rate 2 means in every row there are 2 new columns that have been added, and similarly 2 new have been added in the rows as well. So this filter represents a convolution with dilation of rate 2. So these 2 layers, which had a regular 3x3 convolutional filters, they have been replaced by these dilated layers. So that's one change, and with appropriate padding so that the size of this doesn't change. And then C6, the fully connected layer, has been replaced by a convolutional layer. And not only that, the convolutional filters that are used in this layer, they are dilated convolution with a rate of 12. So if you look at that filter, it would look something like this. And next, they have also replaced the fully connected layers. You remember these 2 layers in the end were fully connected. They have replaced it with convolutional layers of, containing 1 by 1 convolutional filters. And this is the standard technique we have been using whenever we want to change a network to use arbitrary sized image. We do this change, right? We change the fully connected layers to convolutional layers. So this is not surprising. The important things are these C4, C5. They have been replaced with dilated convolutional filters, and the max pooling part has been removed, so there is no downsampling. And finally, this one has a dilated convolution of rate 12. So far so good. We got a feature map which is of size 28 by 28 by n. N is the number of classes. After that, we do a bilinear interpolation. We literally upsample the image by 8 and we get the original image size back. So if you multiply 8 by 28, you get 224. And you get this upsampled image. We could have stopped there, but they wanted to get some better results. This is a toy example. This map is not a real example. Let me show you what a real example looks like. So here's a real result. This is an image. If you train it and pass it through this, you will get this output. So the pinkish color, it represents humans, and the green one represents bicycle. Pretty decent results with this network, but they added one more step which refines these results, because even 1%, 2% change in results, they can make you the state of the art versus not the state of the art. So every little thing counts. So they added this fully connected conditional random fields. We are not going to go into the details of this layer. It is kind of tricky. The reason we are not going to go over the details of this is that it's not essential, as we will see in version 3. So what it does refine the results slightly, and it gets slightly better results. Look at this example. If you look at the results at this stage, this is the result, and output after this stage is this. You look at the person's arm here, you can see that this has a slightly better segmentation right in this region. And you can also see the segmentation in this region is better. The background is clearly visible here. So there are these little changes. You get slightly better results by adding this additional layer. Now, this was DeepLab v1. DeepLab v1 and v2 were both published in the same paper. And the difference between v1 and v2 is this. So if you remember, we had introduced this layer C6, which consisted of many filters having the dilation rate 12. Now, we get some feature map here. The idea here, it is called Artuos spatial pyramid pooling. It says that whatever feature map we get here, we can look at that feature map at different resolutions by changing the dilation rate of the filters used. And we should be looking at this feature map at different resolutions to make a decision, right? So we have multiple versions of this C6 layer with different dilation rates. So we have one with 6, 12, 18, and 24. In version 1, we had only one of those. It was R equals 12. Now, the other layers remain the same. These are both 1-by-1 convolution. It increases the processing slightly, but they also get better results. Now, all these results, they are summed up and then fed to bilinear interpolation, and then you have the conditional random field again, and you get the output. DeepLab v2 did give slightly better results than v1, but right after that, they actually published another paper with DeepLab v3, which was a very similar architecture, except that they removed this final layer of conditional random fields because it did not produce better results when things were tweaked a little bit. So again, the architecture remains about the same. What they did was they replaced the filters in this layer by standard convolutional filters, and they just added dilated convolutions for these 3 layers with dilation rate of 6, 12, and 18. And they noticed that when they used dilation rate of 24, the results actually got slightly worse. So they removed it. Now, you may be thinking that how are they coming up with these architectures, And the answer is that it's trial and error, right? Why didn't they come up with V3 in the V2 paper? Because experimentation takes time, V3 is actually simpler than V2. So sometimes it just takes time to experiment with different architectures to figure out which works the best. Now let's look at the results. The results that came out of this paper, they were just astounding. This almost looks like the ground truth. Here, for example, there are two classes, motorbike and person, and it does so well. Similarly, in this very complex background, it's still able to get motorbike and the person. Similarly, in case of airplanes, it does a very good job. In case of these dogs, it does a very good job. Now, keep in mind that this is a semantic segmentation algorithm. Wherever there is a dog, it simply says that it's a dog. It doesn't give you the boundary of each dog. That would have been an instance segmentation algorithm, or we would need to use some trick like the one that was used in the UNet paper. So that is why you see that everything is one blob, which is dog. These are some other results. You can look at the paper, which we have linked with this video, and the results are stunning. So that is all we wanted to cover in this video. If you have any questions, please ask them in the course forum. Thank you so much.